Welcome to another episode of the Common Lisp Study Group. I'm your host, Ron Baden with Atlanta Functional Programming. I hope your Monday is going well and you are enjoying, at the time of this broadcast, the ending and the recorded stream of the European Lisp Symposium that has occurred earlier today. We are now at 8:30 p.m., 8:35 p.m. Eastern Time. It happened at 10 a.m. in Zurich till 5, 9 till 5 actually, but the keynote was at 9:45. It was a very interesting talk. I'm still not finished with the stream. Still gonna go through it. I may end up doing a recap of the European List Symposium on the study group just so that, it would be useful for us to go through. But that's not what we're going to be talking about today. Um, Last couple of weeks, we've been talking about low-level efficiency issues in Common Lisp. Today is our continuation of this discussion, particularly in Chapter 10, on the topic of avoiding consing. All right, this is probably something that many of you may have encountered when you were starting to write code in Common Lisp, at least in the early stages. Certainly, Practical Common Lisp did bring it up in its introductory chapters on consing and the effects of using consing, how expensive it is. Uh, and a lot of these were kind of related to the topic of garbage collection, which is something we've kind of brought up back and forth on this, going through Common Lisp these 7 years since I've started this broadcast, but we never really sat down and kind of talked about garbage collection in general, mostly because of the fact that uh, by now, especially given the popularity of Java being available, as well as other languages that have some form of garbage collection in them, the topic of garbage collection using garbage collection is a lot of the stuff that most people talk about directly applies to Common Lisp as well. The thing to note, though, is being this is not to say that we did it first here and bringing up a kind of a rant. This is more of a historical consequence that needs to be addressed. Common Lisp, being the first language that really had garbage collection, ended up being kind of a research ground for different garbage collection algorithms, and as a result, some of the garbage collection algorithms and their efficiency issues were brought up and addressed and even reported in this book when I was actually talking about looking into some of the examples that uh, Dr. Norvig was going to go through, and we're going to be covering them today. The one thing to note about the historical pieces against garbage collection inside Common Lisp is that a lot of them either have been or are in the process of being addressed in most modern Common Lisp implementations. Please take note of this, okay? There's a specific quote in the book that talked about early Lisps having unreliable garbage collection to the point where users turned off garbage collection, ran their Lisp system until they ran out of memory, and literally rebooted the machine in order to clear up everything um, in their Lisp image and start from scratch. This does not need to happen today at all, and that's because and the reason is because those early Lisps, com- unlike many modern Lisp implementations, were effectively implemented on real memory. All right. So think, instead of virtual memory where you have a page of physical to virtual addresses mapped together, and you page out and page in memory using your virtual memory manager to kind of have new um, sort of physical addresses mapped into virtual addresses inside of your process. Those earlier systems actually ended up having a way to say, go to memory address 5 and get me the con cell that's at memory address 5 and keep that in memory, unless you're doing garbage collection where it goes in and actually clears the bits in that memory. But again, like I said, those early Lisps, because of how bad the garbage collection was, and most of them were doing modified mark and sweep, they weren't doing what we call compacting garbage collection. Uh, they were very inefficient, very unreliable, and a lot of times you ended up having leaks and at the cost of even worse performance. Right. That said, um, in general, there are some things that this section talked about in terms of avoiding consing because that's kind of the root source of all the garbage that we kind of want to go through. One is, I think, something that most people are aware of, but in case, let's just kind of do a brief review. Um, is the use of destructive operations versus um, non-destructive counterparts. Okay, so what I mean by that is I'm sure as many know, but in case if you don't, as a review, usually when you're manipulating lists, and this is usually or when we're talking about consing a lot, you end up using things like append and remove and to remove items from a list. And what was the third one that was kind of brought up typically? Reversing a list. There's also a reverse algorithm that you can end up doing, right? And all of these are pure functional functions, okay, as in functional programming. And what I mean by that is they do not actually modify the data. They take in a list and they return a list, okay, usually by copying each of the individual values. Now, based on certain performance metrics, it might be the case because you're copying a lot, these operations may need to be replaced by their destructive counterparts, mainly for append, I believe it's nconcatenate or nconc. For remove, it's delete. And we could see delete being here in the destructive operations that takes in the list. And this is just taking an item in a sequence from the to replace to delete that particular item. Okay. And again, these are all in place algorithms. And for reverse, naturally, there's n reverse, right, which is also a destructive version of reverse. In all of these cases, there are potential situations that you might encounter, specifically. The efficiency gains might still lead to errors in certain edge cases in your code and application of those code that might end up becoming extremely difficult to debug. All right. Um, most um, copying can be eliminated by simply changing the way your code is structured and the code executes. And we're going to go see a couple of examples, some of which many of you may have seen here, but others certainly are things that I found interesting that this chapter brought up. Um, One thing that will be necessary to recognize is on top of all this, the um, the advice from chapter 9 regarding choosing the right data structure also comes into play. All right. So one thing that the author brings up is the use of vectors over lists. And we're going to talk about vectors a lot more in this chapter and the use of certain features of the vectors that I'm sure most know but haven't actually taken advantage of in larger scale situations. But as we apply them to later chapters, they'll become very, very important. And I'm talking about things like the fill pointer and allocating memory ahead of time using the vector instead of the list. These kinds of things will end up helping you a lot in adding performance gains into your code. The other thing to be aware of is you could, in some cases, um, reuse specific values that you've accessed already rather than creating copies of those values. So that way, in your particular use case, you can actually not have to worry about adding additional memory overhead simply because you wanted a more reliable function call that may or may not end up into a library call that you will call elsewhere. There are these things that most people do just for in the name of software engineering that does create more maintainable code, certainly, but that might end up being at the cost of performance, and it's something that always needs to be carefully considered before used. All right. Um, so the first thing we're going to be talking about is actually this reorganization of code that I was bringing up earlier. And this is also directly related to what I was talking about in terms of choice of data structures, but we'll be, kind of building up to that. So we're going to go back to the example that we may earlier have seen in many cases, the classic flatten example. And for those of you who are not aware or may not remember, an example of flatten is, one second, is something like this. If we call flatten on a list of sublists A, B, C, and D, this call to flatten will certainly create A, B, C, and D. Now, basically, this is implementing nconc, but there are some reasons why we may end up writing some code like this, uh, just based on some use cases that you may encounter, right? And this one is pretty simple. We have three cases to consider, right? Whether the first case is naturally, and we could write this very simply using um, a cond. So the first case is naturally, are we dealing with a null list, which we need to actually be able to pass in. And here, if we have a null list, we could certainly end up just returning nil. Okay, and then next is obviously if we have an atom that's being passed in to the has into the list itself. Well, the flattened version of an atom is nothing more than a list containing the atom, so we could just simply pass that in like that. And then the last one is naturally the base case, which means you have a list of lists, and you could simply go ahead and say append flatten list with flatten rest list, right? And we have to say actually not the list, but the first of the list, right? And then, so we could check this guy out and we could see what this looks like. This is going to be, of course, if we do A, B, C, and D, this is going to be A, B, C, D like we expected. But this actually is going to be extremely expensive. The reason is I think most of you are aware, each call that's being called in here is effectively going to cons a new list for you. And then you're gonna take those resultant lists and then pass them into append, which itself will cons a list, right? So for a list of n sublists, you're going to create up to a quadratic number of conses just by the sheer number of recursive calls you've done here. Naturally, we don't want that, right? Even if it's semi-efficient, you're going to be potentially using a lot of space. So we want to be able to actually improve on this, right? So you've seen this approach in the book kind of brings this up quite a bit is the use of the accumulator, right? The accumulator pattern, I like to call it, and that is essentially instead of actually calling append and creating pure lists, then sorry, instead of calling recursively flatten and creating these intermediate lists that will then be passed into append to actually do the appending and combination, we will instead construct the list as we go along. And you will see the difference in how this is going to look. Um, so let's see how this looks like. Okay. So our first thing to do is I'm going to just create the flattened ACC version of this, and we have our list input again, but we pass in optionally an accumulator. Okay. What does this accumulator do? Well, most of you have seen accumulators, but in case you haven't, an accumulator is nothing more than an object that's holding the intermediate results at the current recursive call that you've actually passed into. Okay, so now we have this, we can actually go ahead and write our condition, right, or condition, so our cases. So again, we have list being null. What do we do here? We're just going to go ahead and return nil here. Let's go ahead and say if we have an atom passed in, well, what we could do is we will cons the current list with the accumulator. Okay. Um, and so we're always doing almost effectively a prepension of prepending of the list on the accumulator. Oh, my apologies. It's not nil nil. If we have a nil here, we have to return our accumulator because that means we're done. And we can actually get our empty value. So on the empty list, if there is nothing, then the accumulator itself is going to be nil. So we don't have to worry about that. Now in our default case here, what we do is instead of calling append, we call flatten first of the list, and then we're going to pass optionally the flatten of the rest of the list with the accumulator. Okay. Um, and what this does is this will end up connecting them after the recursive calls have all been dealt with. Okay. So rest of list and our accumulator. And I just heard a question being posted. Give me a second here. Do, do, do. Oops. Thank you. Uh, flatten ACC. Right, correct. This is going to be right. So let's see how this looks. Instead of flatten this example, let's call ACC, and optionally we will pass in just an empty list here, and we get our ACC, our same results as we had before. But if you actually look at the disassembly of this, here's flatten. You won't see necessarily the con cells being generated here, but you could certainly see that the recursive calls and the recursive nature of flatten does make it more difficult for the code to get optimized from the standpoint of allocation, right? Um, and this can be, sorry, this can be, oh, sorry, this can be seen here just when you look at how we're calling flatten recursively and the number of moves here. These moves tend to be associated with calling um, and consing information that we need to go and access. So we're actually moving that information into the appropriate registers before calling flatten. Um, and I'm not talking necessarily about the stuff that actually sets up the stack frame, right? I'm talking about more of the C move B stuff that actually grabs the intermediate results and pushes them into the this memory location. All right. So that's one thing, and we could look at the number of bytes. Those who don't necessarily understand the x86 that's being spit out of it, don't worry about it. I'm just showing the disassembly to illustrate a point, which is the size of the number of instructions that actually had to be executed for flatten versus, say, um, if we disassemble flatten ACC, and we end up getting something a little shorter, but nothing um, too major. There's a 30% decrease, certainly, but that's due to how it was able to recognize that we wrote effectively a tail recursive function, and it was able to convert that into a set of a loop instruction here and write the kind of code that you would normally get when if you actually use kind of like the loop macro to actually write out your code. All right. Um, So this is particularly useful to be aware of. Uh, but this also illustrates what I was talking about earlier because the amount of garbage that, and we can actually see if I could create something more of an example where I think I could do this way. Give me just a second. If I do map can, I think I could do map can. Then just take lambda x, and instead I'm just going to return x. And then what I'll do is, oops, let me do this. It's not a list. Loop 4x up to 10, collecting x, and no, it is, maybe it's mapcon. No, that's giving me the intermediate list. Then it has to be, let me see. Oh shoot, my apologies. I accidentally did an A there. Oh, so then I'm surprised map car would actually do this, but that's okay. Let's see that. Yeah. So I could certainly do this. Let me create a quick function here, just to illustrate this kind of benchmark um, on the consing. Let's do a quick define generate data on, and let's call this list of lists. List of lists, and we'll say uh, uh, this is going to be our limit. Okay. And what we'll do is we'll just grab this map car guy I just created and add that. So we now, instead of this, we'll do lim. Okay. And what we'll do is we will call time flatten on generating list of lists up to, let's say, 1,000 objects. So actually, these are all integers. So let's make it even bigger. Let's say 10,000. Okay. Okay. So if we actually go up here, we could see um, that CPU seconds are nothing. They're literally nothing here. And yet we've actually allocated about 982K. All right. Um, so a lot. So for the same experiment, 982K, keep that in mind. Let's try what ACC is going to give us. It's going to give us the same result, but you can see that the difference is about 982K versus 655K. So you're looking at a 30% reduction. And because of the lack of consing, all that I/O, we were able to boost up CPU time from going from 33%, which is what we saw, to 100%. All right, and this is kind of the difference between um, creating an accumulator-based function versus a function that is just purely recursive and you are consing. All right. It's important when we start dealing with larger scale systems in AI, in this book especially, where performance is going to be important for you to kind of memorize. This is something that I've recognized for you to actually almost has second nature. Try and see you can leverage using an accumulator in some way, shape, or form when a recursive function is going to be created, just so that way you can avoid some of these this overhead. And if even better, if you can use the destructive operations that are already in the standard library, hats off. I think you're off to the races. You'll be able to uh, do some really good well, you'll be as performant as it can be, right? It depends on what you're trying to do, but certainly those Lisp implementations tend to be quite fast for the standard library functions. Um, so we talked about garbage, and we also talked about earlier garbage collection systems. So another note that I have here regarding garbage collection that I'm just going to briefly mention is so-called ephemeral or uh, generational garbage collectors. Uh, and this is because of the fact that these systems that have those kinds of garbage collectors tend to uh, be very proactive in deleting short-lived objects. And the space, a lot of actually more modern garbage collectors are generational in nature. Okay. And this isn't talking, this goes back all the way to even concurrent mark and sweep that was introduced in inside Java. Um, although some of those have came out of, I believe, CMUCL and its research into this topic. Uh, although they've obviously innovated since. And the one thing is with ephemeral garbage collection that needs to be at least thought about is when an object in your older generation that's about to get collected ends up getting updated to pointing to newer generation objects, mainly because if that were to happen, you've effectively created a performance bottleneck because now the GC has to be smart about what garbage you're collecting and what is actually pointing to prevent potential um, leaks in various shapes or forms. Now, if you did the other direction, so if a newer garbage collection, uh, newer generation object gets pointed to an older generation object, sorry, if a newer generation object points to an older generation object, um, it's going to be faster because it ends up allowing effectively stuff that could potentially be garbage collected to not accidentally delete um, newer generation objects that are currently in memory. And more importantly, the if you think about what happens if a newer generation object is pointing to an older generation object and the older generation object gets deleted, the newer generation object is basically pointing to nil. All right, it will get updated to be pointing to nil. So it's actually a fewer instructions uh, to actually go and do that removal than the opposite. And this is also one reason why you want to profile your code because in some cases, even though you are trying to avoid consing, because of how you're trying to destroy the object, consing might be necessary and might be faster performance wise than um, the opposite direction. So this is a point that I thought was pretty interesting to be aware of. So we're gonna go and look up Eliza because there's one thing that I wanted to bring up regarding this, and that is, let me just pull it up because the book talks about this, and I thought I had it open, but it looks like I do not. PIP-Lisp, okay, Lisp, Eliza. Okay, so the pat match function, pat, well, I might be using the wrong Eliza. Eliza 1, yes, yeah, there we go, pat match. Okay, so the original pat match function that we saw in Eliza, this one here, ends up being very cons centric because of how we're leveraging the associative list, which causes some issues, right? Now, for those of you who are coming in here from other languages, what I'm about to propose is something very similar to uh, data oriented programming because the version of pattern match that Dr. Norberg mentioned here about using um, two sequences, which I believe is, give me a second here, is um, this version, Eliza PM, pattern matching, pack match. Um, then here is pattern matching version with segment variables. Okay, so this is this is not the same one. Let me go and pull up the other one. Um, well, let me try and describe this since we're running out of time. Instead of trying to hunt it down. So instead of actually doing this consing that you see where you have a cons pattern here and cons pattern input here, what you could do is you could use two sequences, basically two vectors that are indexed, and then what you can leverage is you could use a loop instead of that to go in and check to see if the input and the output is already a vector is going to be this is going to be simple line 25, right? And what you could do is you could actually change the recursive call to actually just access the specific pointer offset into each of the individual vector pairs to actually go in and pass into pattern matching the pattern and the input before you actually go ahead and do the substitution. Okay. Um, this will take more than, it will take less space and the computation will be much faster. All right. Because of the fact that you're just doing an offset calculation. Um, the nice thing about this is um, well, there is one limitation to this, and that is when you allocate larger and larger vectors and you're accumulating the results, you have to potentially copy over existing values in order to add your new data. Now, in Common Lisp, just like most dynamic vector libraries, there is something in Common Lisp called the fill pointer. And the fill pointer is something we've talked about, but we've never actually uh, leveraged in many of our applications and exercises that we've done over the years. But so this is going to be kind of like a first maybe time that we're going to actually leverage it or to show off its capabilities. But to think about what a fill pointer is as the name indicates, um, it's going to fill up um, your vector. Okay, so vectors with fill pointers, the way Norvig describes it is like it's the intersection between a vector and a stack. So you keep pushing elements onto like a stack, and then behind the scenes, if the capacity is filled, the vector will automatically allocate um, a new allocated memory segment, and it'll copy over whatever element, if necessary, into that new memory segment. So you end up effectively increasing the capacity behind the scenes while maintaining a very clean interface for you to actually go and check stuff out. Okay, so let's do one thing to kind of like show how this works. Um, okay, so we're gonna create a new parameter. Okay, called test array. And what we're going to do is we're going to call make array. Make array is what you would use for this. Okay, we say our dimensions is going to be just 5 just to start out with. Okay, and we will say our fill pointer, which you can see here in the signature, okay, is going to be set to 0. Okay, which means there's no fill. Okay, cool. Now we're going to also um, just like in Actually, let me double check to make sure this is here. Print array is set to what? Okay, print array is set to true, so we're going to be able to set the results here. Okay, perfect. Okay, so let's go ahead and do what the book kind of suggested, which is vector push. Okay, vector push test, sorry, new element. Let's call it 0. Okay, into test array. Okay, now all's good. All right, if we pass in a, all right, if we try and figure out what test array has, we'll end up um, having 0 as our vector. If we pass in 1 into test array here, we have, again, in test array, 2 elements out of a capacity of 5. Okay, now let's just go ahead and add 10. Let's see. Yeah, let's do this 10 times. Okay, and what we'll do is we'll do vector push extend. Okay, and we're just going to add a symbol in here. They used X here into test array. All right. So now, if we go and take a look at test array, we'll see 0, 1, x, 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 right? Additionally, if we call the fill pointer to see what to get the fill pointer is of the test array, you'll see that the fill pointer is now set to the 12th index. Okay, and that makes sense because we have 11. We have 12. We have 12 elements here. So we're the 12th index is representing the 13th element that needs to be inserted, right? Because we're using 0 style indexing here. Okay, so 3, 6, 9. Sorry, 3, 6, 9, 12. Right. So that fill pointer makes things pretty useful. Now, what's interesting is you can manipulate this fill pointer, right? So we can actually this is set effable, right? So we can actually go ahead and do fill pointer test array, and we can access any element in the list that we want. If we choose, for example, this, and we do test array here, you'll see that we've effectively gotten rid of everything up until that point. Okay, and test array is now set to, again, the second element. Okay, so if we try to find what we just inserted into here, you end up getting nothing, right? Because there's nothing there. Additionally, if you try using aref to access anything beyond this, you'll get an error. All right. Ooh, wait a second. That's interesting. Oh, sorry, my mistake. I misunderstood what they said. So find itself can't find anything past the fill pointer because the fill pointer is what it uses to actually determine if it's at the end of a list. But aref can actually see beyond it, which means you can actually see the garbage if you end up leveraging aref. All right. So that's a little bit of a bummer, but there are advantages of leveraging vector with fill pointers and so forth. One thing he brought up is about um, the stuff with fill pointers is the contents of the vectors can change. So calling functions need to hang on to return values when especially, and this is especially important when you are using it in the case of our recursive call to pattern match. So that's something to be at least cognizant about. Okay, but most of you who come from other languages are very well aware of these. These are basically your extensible vectors. Okay, and they're very, very efficient in Common Lisp. It's actually surprising that it's not used more in the standard library than it is, but that's more of a historical consequence, I believe, than anything else. They've had vectors for a very long time inside Common Lisp, at least as long as the standard's been alive. So, in this book, bringing it up again, this book is pretty old. This is in 1990, right? The fact that he leverages them quite a bit is, but most modern implementations of standard library still goes back to Consing, means there are some historical consequences that are preventing some of these more efficient data structures from being used in the lower level infrastructure inside Common Lisp. So at the application level, you could certainly use them and get the benefits, but they may not replace core data structures at all. So just keep that in mind. Um, let me stop here and see if there are any other questions. Okay, nobody on YouTube is asking, and we are good. All right, let's go to the next thing. Um, so the book brought up something that that was pretty interesting that I wanted to kind of go through, and this is the unique cons function that the author has written around. So let me kind of see if I can give my understanding of this section. So reusing con cells, okay, can be created by simply um, so let me rewind a little bit. So we talked about vectors saving garbage, all right? If and in a lot of cases, replacing a list with a vector because they're both sequence objects will save you a lot of garbage from being created. Okay, but because of the flexibility of lists, there might be some edge cases where a list is very appropriate naturally, but you don't want to necessarily pay for the cost of using cons on the list functions, right? So, um, Dr. Norvig created this function called reuse cons that that effectively does this thing that allows you, has the name again indicates, it's going to be reusing these functions. Okay, um, and the function goes something like this. Okay, so first we're going to go ahead and proclaim this, and we want this to be inlined. Um, Inline reuse cons. Okay, and reuse cons will end up being a signature that takes two arguments. Okay, actually three arguments. One is your x and y that you want to cons necessarily, and xy. Okay, this is just an accumulator. Okay, um, what you do is basically you take in if, okay, the car of xy, which will represent a potential cons pair, is equal to x. Okay, car of xy, sorry. No, not this. There we go. Car of xy is equal to x, and the coulter of xy is equal to y. Then what we're doing is we're going to only return xy because those values are already members of the consoles that we're trying to actually look up. Okay, so and this is going to be used in the case where when we were doing like pattern matching, we could leverage this kind of thing to um, check to see if we need to necessarily create a new pair that's in the associative list by just looking it up and seeing if we can reuse the console that it represents. Otherwise, what we're going to do is it's saying that this is a new cons pair, so we could just go ahead and create that cons pair, that dotted pair. That's all this function is doing. Let me go ahead and do this. This is now defined actually in PAIP, but I thought I'd at least bring up what what the code looks like. But what's interesting to note about this is this sort of definition, okay, um, can be used to rewrite some of the standard libraries functions just to leverage the reuse cons and then preventing any additional cons from happening. All right. And so there's an example called remove on it actually replaces a standard remove, but it leverages the reuse cons that we've just created, and it's leveraged in the book. I bring it up mainly because there are still some applications where without you passing in the console that you're trying to um, uh, reuse, okay? Um, because one of the limitations of this is you have to have a console that you can do a comparison against to a console that you're constructing. And so the only time the space is actually guaranteed to be saved is if the required console that you're passing in into reuse cons is equal to the new cons pair that you're trying to generate. So there are some cases where this is true, but not in all cases, right? So you may actually want to create an actual real cons pair, a unique cons, um, for every console without having to actually pass in that hint console for comparison. Okay. Um, the way you could do this is actually creating, and this is the one thing that I wanted to kind of the way the book actually addressed this is by doing the following. First, they created a unique cons hash table. Okay, so make hash table. And what this is doing is it's going to end up, and it uses also for folks who want to, it uses EQ equality for checking the key. And what this does is it is going to be leveraged by this ucons xy function that simply implements cons the following way. Oh, I'm writing the wrong thing. I need to create this a let. And um, what we'll do is um, we keep track of the all right. So what we do is we keep track of the car table as being not table as being the get hash. So either we've already created um, the or we created already the get hash of x inside our unique cons table. Okay, unique cons table. Okay, or we don't have an entry in there. We need to actually go in and set f get hash on the unique cons table. Okay, and we're going to create a new hash table that represents this pair. Okay, make hash table with the equality. Okay, and we're doing it on the first key. Okay, and then when we have this here, we go in and we just do or get hash y from the car table, or we haven't actually gone ahead and gotten it. So we have to do a get hash y car table. And what does this hold? This will hold the actual cons value that the cons pair that we actually want. Okay. So with two quick lookups into this hash table, which is a two-level hash, we get a reusable con cell that we could guarantee to always be unique for a given combination of pairs. All right. This here I know looks like it's a lot of work, but if I understood the reasons why this is preferable in some cases, is because it's guaranteed, it's idempotent. It's guaranteed to always give you the same exact cons pair for the same exact inputs, right? Which you may sometimes need, especially in hashing situations, to guarantee that um, that the cons pair that you're leveraging that you've hashed is a cons pair that you're modifying or you're needing to do certain information on, right? So the reason why this was a bit confusing is he ends up leveraging this to write a bunch of unique functions that I think I understood, but I'm still kind of working through it, to be quite honest, as to why this is particularly advantageous. Um, the main thing that he brings up that I do kind of agree with is in the application of indexing. And that is if the lists are unique, then you could throw them into a hash table, and the hash table will be a constant time lookup instead of the number of indirections that you end up having to deal with when you're actually iterating through a list. All right. But all the other stuff that he implemented, like append and stuff, that's kind of something that I I'm still trying to wrap my head around as to why he would need to use this or why we would need to do that. Um, So, um, I'm just mentioning this ahead of time. Like this particular section was a little like, okay, I guess that's fine for some cases, but when you're doing indexing, but in all the other cases, it seems like it's a lot of overhead. Um, I mean, once you've implemented it the first time, you don't need to implement it again, but it just seems like it's a lot of overkill for your general level applications. But it was interesting to note, so I just thought I'd kind of bring it up. Um, let's see, what's the two? So there were two other applications that I'm just going to briefly mention here, about using avoiding consing for multiple value returns, versus uh, parameters. So the example that they gave is, let's say that you have a, a point. Sorry, you made a struct using a point. Okay, and so x, y, and z here, and we do a scale here of the points. Okay, so you pass in some scaling factor in the point that you're trying to scale, and you create a new point. Okay, and for x you pass in, you know, times k point x point, and you have to do this for, oh sorry, do this for y, and z. Okay, and what we do is here, instead of doing this, which will be potentially expensive, um, by just simply returning um, for, so instead of doing a structure and another structure, you could just simply do scale point, scaling factor x, y, and z, and leverage multiple values to actually go in and take care of that for you. And one of the advantages of this also is then you're also getting destructuring bind for you, so you can actually leverage destructuring bind to actually leverage, well, not leverage, provide the facilities to effectively do the same thing that one would end up doing with objects or even defstruct, which is multiple with what was it? It's called with slot values. Um, so you could do, for those who don't remember what with slots, where it actually effectively does the same thing as destructuring bind, but that's for objects by looking up the object definition. But this is more expensive than just using destructuring bind with values, is my understanding. Finally, uh, we're going to be talking about resources, um, and their particular dealing with Common Lisp's consing infrastructure and memory management. Now, most of you are aware when I say the word resource, but in case you're not, I'll be very explicit here. The book, when it's talking about resources, it's talking about some data type or object that needs to be kind of managed. One of the typical examples or canonical examples for uh, resources when we start talking about is file pointers, all right, or sockets, or which is technically also a file pointer when you start thinking about it in Linux terms, or database connections. These are all resources that need to be explicitly managed. Um, and there are cases where you really want to explicitly manage it because uh, a lot of times, and especially this happens when you're dealing with database connections, You're just trying to run a query on a particular database, and you have the connection open, but it's a short-lived connection, and you may just require it for every request. So rather than constantly creating it, run the query and closing off the connection, managing an explicit pool of these connections would be very, very useful, because then you're avoiding the overhead of actually going to check to see if the database is available, going to check to see if you have to retry and all this, which will take time naturally away from you just running the damn query. Um, Additionally, um, you can guarantee that when instances are no longer needed, they are properly cleaned up. Um, and last but not least, honestly, this is something that needs to be, I don't know why I mentioned, but it is definitely the case where instances that are fairly large, that are big in size, has no multiple layers of indirections. Again, one typical example of this is like if you're writing a game engine and you're doing an asset manager, it's typically a very large structure to do all the asset management, and the initialization of that structure will take a very long time. So rather than you copying this expensive object and moving it around, you might treat this as a single resource and then just leverage it. Okay. Um, so one of the advantages of leveraging a generational garbage collection, um, or specifically using Lisp and garbage collected languages in general, is we try to guarantee no leaks. So you won't have any memory leaks, but that doesn't necessarily mean you're going to uh, avoid potentially resource leaks. All right. And what's worse is modern garbage collection techniques are very highly optimized. Okay. And so still, while these potential deallocations and structures are potential bug sources that have been resolved, and most people who talk manual memory management says that your general purpose memory management scheme is still slower than a user's applied scheme. Um, you It's going to be the case that if you are looking at short-lived garbage with the ephemeral garbage collector, it's more likely going to be garbage. But if you hold on to that same garbage, it's going to become uh, expensive. All right. So one thing that Norvig pulls here is he leverages vectors to actually create fill pointer based resource pools, and he defines a macro called def resource that I encourage folks to read and kind of look into. I'm not going to. I believe actually it's already available, if I'm not mistaken. Def resource, yeah, def resource. And if we go and describe this, where is it located? PIP. I think this is in auxiliary functions. So we could take a look at this very quickly in the remaining 16 minutes, because this is a particularly interesting function when I was looking at it in the book. Augs functions.lisp. The hell? Oh, no, not this. PIP. Oh, wait. Lisp projects. PIP. PIP-lisp. Lisp augs functions. Okay. And let's go look up def resource. Okay. So def resource takes in a constructor, all right? And that constructor is the object that we're going to effectively um, uh, create, all right? So if we used make point, for example, make point will actually allow you to um, generate. So, and I can probably actually leverage this here. Let me just do this. Go to PB level efficiency. If I were to say def resource, or yeah, def resource, okay, and here, and we call it buffer. Actually, let's call this point pool, okay, and um, we will constructor is going to be make point, okay. We want initial copies to being, for now, 100, just for the sake of example, and um, we want the size to being 100, okay. uh, Wait, I mixed this up. We want the size to be 100, but we want only 10 copies, all right. So when we go and look at this macro expansion, you can actually see what we've ended up doing is we created two functions, one called allocate point, deallocate point. This allocate and deallocate, what it does it's doing nothing more than a vector push and a vector pop into our um, uh, resource pool. Okay. Now, for those who are confused as to why allocate is popping versus pushing, it's because of the fact that allocate is getting a resource, right? Which means the pool is losing a resource, right? And if we think about the a resource pool being a stack, then you should get, um, the most available resource first, right? So if we're treating it as a stack, the last one that's been created is the first one out. So we'll end up naturally going ahead and popping the last available, well, the most available resource first, and then we'll go ahead and keep going until the pool is empty. Um, this is particularly useful again in the cases where your resources are expensive. Um, so you're pre-allocating the number of objects, expensive objects that you're going to do, put them into a pool and just leverage them. And the most obvious one that where this will become useful is things that are dealing with I/O. So a lot of your I/O stuff, putting it in a calculated pool would be useful. But the bottom line is once it's allocated, it's a fixed amount of memory, right? So you don't have to really worry about that. Um, the one thing that he calls out that I don't know if it's necessarily applicable today, but I'm going to bring up anyway for you folks, just in case many of you may or may not be using Lisps that have this problem. Using this particular pattern, because we're doing this pre-allocation up front, might put you at odds with the garbage collection and the storage management scheme of the Lisp implementation that you're leveraging. This may not be the case for most modern Lisps because of performance of modern virtual memory and operating systems. But in case you're dealing with something that's soft real time or on an embedded system, or you're leveraging that is a Lisp that has limited functionality, you might be aware of this just so that you can deal with it, right? Um, that's all I had to say about this topic. Uh, I thought I would have time to actually go through the last two topics, which is compiler macros and choosing the right data structures, but I think I'm going to end it here just so that I don't rush it. Are there questions? Honestly, we went through a lot of material. I think for folks who aren't familiar with the heavy consing, I think what you want to do, if there's one piece of advice I'm going to say from experience that I've seen, is if you take your algorithms and you profile and you make sure that you're not consing a lot, all right, that is a good sign that your algorithm is somewhat cons free. All right. In cases that you do need to cons, just bear in mind that there are techniques that you could leverage where the consing is down to a minimal, and that will have an automatic consequence on how your code's going to generate and how efficient your code will be over time. It'll take practice, honestly. Even now, I mess up it sometimes. Being I would say now a intermediate. I wouldn't say even an intermediate beginner programmer in Common Lisp, just because I would say that my Lisp is better than what it was 7 years ago, but it's certainly not as good as it could be if I was working on it every day and not switching between languages. Anyway, with that, I'm going to end today. Before I let you all go, if you like our material, please hit the bell icon, like and subscribe to Atlanta Functional Programming for Talks. We're gonna be out for the next 6 weeks for a little hiatus. We will reconvene in July. Um, I will and and we will continue and finish off our compiler macros and data structures discussion then. Sorry for the long wait, just because there's a uh, bunch of plans the next month that I have to take care of. But with that, enjoy your evening, and I'll see you guys in a month. Thank you for joining. Peace.